wrong. Can you see something?
Perfect. Yeah.
Yes,
Cool. Hi, everyone. Thanks very much. I'm super delighted to be part of this amazing program. There will be less math introduced in this presentation, but I think maybe it's a nice mix, actually. So today I will briefly talk about a side project of mine and another team member that we've done since August until beginning of this month. We're still working on a publication. It will be on semantic answer similarity metrics, which I'll introduce in a bit. So, okay, there is some delay. We'll start off with giving a rough overview of a generic pipeline, QA pipeline, in the context of natural language processing. If I was in the audience right now, apologies, I couldn't be there in person. I would ask how many of you have ever got your hands dirty doing some NLP, so trying to solve some NLP question task. But this is effectively using natural language processing techniques to do automated question answering. And then we'll briefly define what semantic answer similarity means for us anyway, which will be followed by introduction of some of the models / approaches used to attempt evaluate that or approximate that. And we'll delve a bit deeper into those scores to give a better sense. And then we'll naturally ask the question, like, how deep should we go? I don't know, maybe some of you have seen the popular meme from Inception asking this question, but it's a very classic question that everybody has to ask when dealing with neural networks. Then there will be some qualitative study about the errors that two out of four approaches that we'll introduce. And we'll wrap up by summarizing our main contributions and what is their, what future holds for us and others in the field, really. So question answering, in my honest opinion, is a predominant area, if not the most important area in natural language processing going forward. Because asking questions is something very natural to humans in general. And we're slowly moving towards natural language understanding. So trying to make models not just give the answers we expect, but give them in a way we expect. So if we could teach algorithms to answer questions, it could really ease workload in so many different fields and subfields that I'm not gonna, count all of them. But the way it's approached in NLP is the following. We have all sorts of massive data sources, Wikipedia, reports, financial reports, sustainability reports. We have Twitter, other social media content, and the speed at which the amount of textual documents increase is probably faster than exponential, right? So we need a model to effectively give us more consumable, relevant documents among all this unstructured data. That's the first component. So that's, can you see when I wiggle around something on the desktop? I think so, right? Yes, no, thumbs up?
Yeah.
Cool. And then the next model, the second component, main component of this pipeline is once you have all the relevant documents to extract the span that contains the answer to the question asked. Well, that's one simplified version of the pipeline anyway. There are all sorts of approaches, but this is enough to get an understanding of what we're going to describe going on. So the way a lot of machine translation, natural language generation works is you need to understand if your model is doing something useful or not. And the status quo is to use some kind of lexical overlap metric. So be it blur or exact match. Exact match is doing exactly what it's doing, what you think it's doing. So it's comparing two strings if they are identical. It gives a score of 1, if not 0. Then a slightly better version is blur score, which looks at n-gram overlaps between two strings. So they have, there is quite a bit of criticism that one can think of. For example, what if the two answers are identical? Well, they both answer the question, but they are written in different ways, or they are synonyms. In that case, exact match will give an answer of 0, a score of 0, not answer, score of 0, and blur will give a score of 0 if there is no overlap. I can think of another edge case in which actually there was one ground truth answer, and there are two answers, very long answers. One is wrong, and the other is correct. It's just not phrased using the same substrings. So the wrong answer will have more overlap with the ground truth than the correct answer. So this is just two simple edge cases that I can think of. And we need something to solve this problem effectively, not just to be aware of how models do compare to each other, but also, so that's the fairness element, but also to use it as an evaluation metric to improve existing models going forward. So effectively, this work is developed as an evaluation of another work, another paper that was, the first version was published in August. It will be part of EMNLP, which is a very kind of respected journal in NLP. And they had 4 approaches. They proposed 4 approaches. So the first one is a bi-encoder approach. What bi-encoder does, it takes 2 answers, feeds them into 2 identical networks, but separate networks. They call them Siamese neural networks. Maybe some of you have heard or used them. And we get 2 embeddings, 2 contextual embeddings. To explain what contextual embedding is, in very simple words, English, for example, is a very, very difficult language for non-native speakers. But even for native speakers, if you try to join a conversation in the middle and you have no context, you might be quite lost. For example, the word set has 72 meanings or something, even in Chambers Dictionary. And without having some reference to the sentence before, it's very easy to get lost of what exactly set means. So that's where contextual embeddings come in. They create a vector representation of a token, which is contextualized. So there is no unique vector representation for every word in the dictionary. I mean, there is, the previous models were solving a lot of NLP tasks using unique vector representations, but we've moved on from then using transformers and specifically bird type transformers. So this is what bi-encoder does. It spits out 2 contextual embeddings, i.e. 2 specific vectors, and then we compare those vectors using cosine similarity. The second approach is a cross-encoder approach. In case of cross-encoder, we don't create 2 separate networks. We create one network, but we take sentence 1, concatenate with sentence 2 with a special token in between, and that's what's fed into an encoder. So we get a contextual, we don't get an embedding out of the model. The only thing that model will give is the final similarity score. That's the second approach. And then BERT score is something that was originally used in the context of machine translation evaluation and natural language generation, shortly NLG. And the way we will compare this to others is with like as is, and after fine-tuning on some semantic textual similarity dataset, shortly SES benchmark. So the way BERT score works is a bit like a combination. It takes the first answer and then the second answer, sends them to a transformer model, gets the embeddings, contextual embeddings again, and then it uses greedy matching. Like, I think you can already kind of see it here. So it uses maximum cosine similarity and greedy matching to then find how many tokens or which tokens in the reference answer are there in the candidate answer, and the other way around. So the first one gives you recall, and the second way of counting will give you precision. This way, then you compute your F1 score, and that F1 score is effectively BERT score. So yeah, we use BERT score in two ways though. One as is, without any fine tuning, just the pre-trained BERT model. And then in the second way, where we fine tune it on semantic textual similarity benchmark dataset. So evaluation datasets are subsets of SQuAD, German Quad, and NQOpen. Don't worry if you've never heard of this names before. SQuAD stands for Stanford Question Answering Dataset, German Quad, German Question Answering Dataset, NQOpen Natural Question Dataset. They are very different in nature, but there are some similarities across them. So all of them contain triples or triplets. Answer, answer, score, answer, answer, score. They were all annotated three-way, and what that means is annotator one would get all answers. So answer one, answer two, give a similarity score, answer one, answer two, similarity score. Then annotator two would do exactly the same. Annotator three would be some kind of a tiebreaker. So they would only look at the cases where the answers didn't match, or the scores, sorry. I shouldn't use the answer in ambiguous ways during this presentation. So the scores didn't match. And the scores were 0, 1, 2. 0 means not similar at all, 1 possibly similar, in the sense that, for example, one word could have one less, could be more specific than the other answer. And it would help if that answer had a bit more description to it. Note that that doesn't include second names, because middle names, because in vast majority of the cases, people can be identified just by first name and surname. But they differ not just in that, because all of them are actually three-way annotated. The way NQOpen is annotated is slightly different. In SQuAD and German code, annotators had answer one, answer two, they had to define similarity. In NQOpen, they had question and prediction of a QA model. And QA model is what I described in the very first slide when I gave you the pipeline. So a model gave the predictions, and an annotator would look at the predictions and define if that prediction answers the question or not. So label 2 means answers correctly, label 1 means possibly correctly, and 0 means definitely incorrect. So the answer definitely doesn't answer the question. So it's slightly different than the two. The methodology difference is something that was actually overlooked by the original authors of the paper. Don't worry, I know it's a massive table, but to basically summarize our findings, is if you just look at Pearson correlation, it looks like cross-encoded metric, which the original authors called SAS, because it was, I assume, because it was outperforming others in many respects. It's giving really high scores when you look at Pearson correlation, but we argue that using Pearson correlation in this context is not necessarily very reliable, at least because our scores are, so the model scores are all continuous, and then the label, human labels, which we will refer to as human judgment, is discrete. We just have 0, 1, 2 labels, right? So using rank correlations is a bit more reliable and a bit more meaningful in this context. But it's nevertheless used quite widely in the field. So we still included Pearson correlation values. So the case of no lexical overlap, which is exactly when F1 is 0, F1 score is 0, is really hard. And that's effectively what we're trying to achieve. So this is the case where answer 1 and answer 2 have no string overlap. But in some cases, they are actually equivalent. And that's what we're trying to find. And you'll see as we quickly go to the model error analysis that by identifying some weaknesses of the model and trying to help overcome those weaknesses, we've actually improved the correlations to human judgment quite significantly compared to cross-encoder, just pure cross-encoder approach. So these are the results for German quad. If you've noticed here, German quad is different than squad and NQ open in the sense that it has more lexical overlap in answers than the other two datasets. What it means is it's less common that answer 1 and answer 2 will have no string matching. So it helps with these metrics, just like with lexical overlap metrics too, not very surprisingly. And this is where how deep should we go exercise comes in. It's interesting because if you don't train the BERT score model, this is, by the way, only for the third approach in the list. If you don't train it on semantic textual similarity dataset, then going deeper doesn't improve it. In the case of no lexical overlap, it's kind of vague if it's useful or not. Like you can see here that it's kind of wobbling in the middle. But in the case of some semantic overlap, actually going deeper hurts in the case of no fine tuning. But if you fine tune it on semantic textual overlap, it improves massively. And the deeper you go, the better your results are. And that's across the board, not just in the case of semantic overlap or lack of it whatsoever. So what it means is, yeah, sadly, the deeper you go, the better. And for the reference, for those of you who have never worked with transformers, the base transformer class, so transformers are now available, pre-trained models are available for free from Hugging Face. And the base one comes with 12 layers. The large one comes with 24 layers. So in our case, maximum number of layers was 12. That's why we extract those contextual embeddings from the last layer. But in the case of the no fine tuning, we extract just the second layer is enough. So we don't go too deep in a way. We've looked at some of the errors in the extreme cases and how the errors were identified. Effectively, you look at label. When the label, for example, is 2, which means the answers are similar. This is, by the way, only for NQ open. So the label of 2 means that the answer is correctly answering the question asked. The major category of errors came from names. And names, not just like human names, but geographical location names, direction. directions, etc. The next largest category was, again, like it's related to names, and that's co-reference. So this is basically an actor's real name and a fictional character name. So we try to solve this problem by by fine-tuning on names in the following way. So we created silver labels. I don't think in machine learning literature there is, we call them silver labels, but what happens here is we use a cross encoder and we feed it name 1, name 2, which are effectively identical, or no, not identical, equivalent. And so name 1 could be Gary Kasparov, and name 2 could be Gary Kasparov was a middle name. So we train a lot of examples like that. A cross encoder will give a score, and then we use those noisy labels to train other models, such as BERT score. And this is effectively what we refer to here as F tilde. So F tilde was trained on silver labels that we obtained by using a cross encoder. And that improved matters quite a bit, actually. And this was, all this work was, bear in mind, this was done in a span of 5 weeks. And none of us are NLP professionals or anything, but we worked quite hard to really understand the underlying problem and how it can be overcome. So to summarize, what we've done is we found a few errors slash something that was overlooked in a couple of places in the original paper, which was reviewed already before us by a couple of reviewers. But the team that published the original paper is an amazing team. They are the sponsors and supporters of the main, actually the only supporters of Haystack Framework, which is a question answering, open source question answering framework that is used not just in Germany, but across the world. I forgot to mention that German code was also created by the same team, DeepSet AI team. So they have been super, super supportive and super open to feedback. So this was an amazing collaboration across the globe, actually, California, Germany, Berlin, and Munich, and London. So we worked together quite efficiently in that sense. Another fold of our contributions are effectively twofold. So we gave our community back a new data set. Not that that data set would be really hard to get. Some people, for example, there is a new paper that mined names from knowledge bases, such as Freebase and Wikipedia. So we were a bit lucky because we didn't have to necessarily mine those databases. We found easier to use names dataset, but we've filtered it down to common names, well, names that are commonly used in English contexts. But we basically open sourced it now. It's all available on GitHub. Another major contribution is relabeling NQ open. If you remember, it had 3,300 samples, which if you're coming from machine learning, it might seem like a small data set. It's not. It's actually quite significant for adversarial training and evaluation in the context of NLP. So yeah, and instead of having multiple configurations of BERT score, which if you look at this infographic, it doesn't necessarily tell you how many moving parts it has, but it has many moving parts. And what we've achieved is make life easier and have one single configuration, which is also, by the way, on GitHub. It's all published. What we are aiming to do is continue this work, but focus a bit more on MQ Open as opposed to focusing on Squad and German Quad. And the main reason is that natural questions is an open domain question answering dataset. And what it means is what people actually ask Google to answer, as opposed to you have a domain specific data source and you're sending queries that are very specific to that domain, and you're sure that the answer will be hidden somewhere in that context. In case of open domain question answering, that's not the case. The question may not have answers, you don't know where the questions will come from, etc., etc. So it's a bit more challenging of a problem, which is why we want to focus a bit more on that problem. And we believe that using BERT score instead of cross encoder is better because it's faster. It's a lot more computationally efficient than using cross encoders. And it might be a bit more useful in industry than cross encoder, in which case we're a bit more inclined to use it. So yeah, that's pretty much it. Unless you have any questions, here are the major references. And here is my teammate from Germany. But unless there are any questions, that's it from me today.
Thank you. Question from the audience.
Some of this research to your work, hedge fund, or like what's?
Sorry, I can't quite hear the question from here.
I can take it actually. So Farida is whether the work can be applied to we have had strategies indeed where we look at NLP applications to financial work. And for example, using particular databases and looking at matching names of companies, for example, would you examples of NLP applications?
I assume the question was about how do you apply this newly obtained knowledge in back at work, if I'm not mistaken.
Yes, so Farida, essentially what I was answering was that broadly had NLP application strategies action.
So just to yeah, sorry, it's a bit intermittent from the audience, hard to hear, but it's twofold actually. So first of all, and not necessarily this particular problem, like maybe you can't transfer it one-to-one, but sentiment analysis is a couple of decades old problem that is very, very efficiently used in finance across the board, especially if you can trade low frequency, high frequency. It's of utmost importance really to have a strategy responsible for getting the sentiment right. And Ravenpack is one of the companies that is effectively making billions a year just of sentiment analysis score publication. That's one. And then the other is less obvious, but I think Sylvia may have touched on it. I could very briefly hear company names, but actually building company trees is something that not many people have looked into, and hierarchies of companies. So this is something that can be basically inferred from equivalence. semantic equivalence.